Hello everybody, today I'm going to introduce the curved length and the curvature. Now, how do we know a curved length of a representation of a vector function r of t? Well, we know that it is actually a parametric equation with f of t, g of t, and h of t. If I treat it as a parametric equation, then I can know its length at ease. The length is equal to, for example, if the time, I treat the parametric as time because easy for you to understand, from A to B. And we know the length is actually equal to, at a small part, it has a change of dx, change of dy, and a change of dz. So it is actually dx over dt squared plus dy over dt squared plus dz over dt squared times dt. And this represents the length at the change of dt. However, we actually know what those are. It is integral of square root of f prime squared plus g prime squared plus h prime squared, right? And what is this? This is actually the magnitude of r prime of t. Well, now we know a way to figure out the length of the curve. And what's more, we can know from this is that L is a function about t, and it actually is the integral of r prime's, the magnitude of r prime. Therefore, dl over dt is actually r prime. Well, how can we use that? We'll see that later. So right now we know that the r prime is a unit, which we can see on the diagram. This is r, and this is r prime. So adding all of the r prime's magnitude, we get the length, and that makes sense. So let's now move on to the curvature. And curvature, what is curvature? We want to know how sharp is that for at one point to change. And if the curvature is equal to 0, which means it is a straight line. And if the curvature equals to probably infinity, it is sharp. So how do we define this? Well, we want to define it as the change of the unit vector. We use t, we know that in the last lesson, to represent the unit vector of the derivative, because derivatives is how their direction changes. So it is r prime t divided by the magnitude of r prime of t. So what is the curvature? Well, by definition, it is dt over ds and or dl. We use L to represent the length of the curve. So what we are trying to say here is that the change of unit vector per change of length. So if I change a little bit, move on a little bit, how is our unit vector change? That is the curvature. And let's derive it a little bit. dt, if we put a small dt here for both the numerator and denominator, we can get dt over d small t, it is actually t prime of t. And what is the L over dt? Well, we know that it is actually the r prime of t. So it is t prime magnitude divided by r prime's magnitude. So far, we actually can know the value of the curvature, and we use a small k to represent it. It is called kappa as the curvature. Actually, we can derive it further. It is actually equal to r prime's cross product of r double prime divided by r prime to the power of 3. And I would like to call it a 1, 2, 3 rule. The first prime, the second prime times the first prime to the power of 3. 1, 2, 3. And you know how to remember that. Its proof is a little bit complicated, so you can prove it by yourself. Now we know two ways of deriving the curvature of a curve. One is through the unit vector, and the other is use the 1, 2, 3 rule. So that's all for the curve length and the curvature. And I would like to add a little bit more. It's about the tangential and normal vector of the acceleration. As you can see, this is the acceleration and this is its speed. Usually in physics, we fracture the acceleration into one direction and another direction that is perpendicular to it. So this is the thing what we wanted to do here. What is v? V is actually equal to r prime of t. And what is a? At is actually equal to the r double prime of t. So the normal vector, let's see the tangent vector first. The tangent vector is actually a projection of a to v, which is we want to put r2 double prime onto r prime. So we know how to find the magnitude of a projection, that is the dot product divided by this is a tangent component. And for the normal component, we wanted to put it perpendicular to r prime. So we know what's that. It is the cross product. So it is cross product, the magnitude of that divided by r prime. Therefore, we know the tangent and the normal vector of that. However, we can derive something from those two. Something a little bit, I think it's beautiful. Remember what we've done on the curvature? We know that the curvature kt is actually equal to r times r double prime divided by r prime to the power of 3. This is similar. So we can see that the normal vector, the normal component is actually equal to kt times r prime to the power of 2. What is this? This is actually the velocity. I use nu to represent that, nu t. So normal vector is actually equal to kappa times nu squared. Then what is the tangent vector? Well, we might cheat a little bit here. Let's look at its geometric meanings. At one point, this is its velocity vector, and this is its acceleration vector. This is the tangential direction, and we want to know what is the component of acceleration. We know that how the speed is changed at this instant is caused by the acceleration, especially the tangential opponent of the acceleration. So actually, it is just v prime, because it is the tangential opponent of the acceleration that cause the nu to change. So it is just by cheating a little bit. Therefore, we can write the whole acceleration out. A is actually equal to the v prime nu prime let's use a sharp bracket, k times nu squared. This two component is the parallel component and the direction and the perpendicular direction. And I think this is really beautiful. So that's all for the curve length. We have equation to solve for it, and curvature we have two ways to solve for it, and finally the accelerations along and perpendicular to the velocity vector. And that's all. Thank you for listening.